All right, good morning. Physics teachers are awesome, number 89. Today I did a search for physics homework, I think, and this is what I got.
So, let's make up a rocket question. Let's say we have a
Very nice.
So the rocket engine fires and provides I don't know. Let's say the rocket engine fires for 2 seconds.
So right away you can tell that this is just something off the top of his head. And I really like doing this in front of students. Just putting numbers down, feeling like you're demonstrating your confidence to be able to handle just about anything. Sometimes when I do this, I will take numbers from the students. They'll say, well, how long do you want it to be? And it's interesting because I used to sort of carefully sort of think about their answers and say, oh, well, that won't work. How about I cut that by a factor of 2, or actually I think it needs to be 10 times bigger. But I started just using whatever they would say. And I would hope that the other students would say, well, hang on a second. My God, that rocket would never even take off if that was the case. Things like that to get them to be critical of each other, not, in a way that you're being judgy, but just to say, hey, wait a second, but if the rocket only fires for 0.002 seconds or an hour, we're going to have to do something very, very different. I don't know. But this is either going to be a full-on rocket problem where we're going to do constant, a variable mass problem, or it might just be an impulse and then just, like a parabolic orbit or something. I guess I don't know what level this is.
Providing a acceleration of 4 meters per second squared. After the 2 seconds, the rocket engine shuts off and the rocket continues to its highest point.
Nice.
Due to free fall. Now, drawing the picture changes the demeanor of the question. If I didn't draw the picture, you might understand that there are parts to the problem. And in those parts, you may not be able to see the details unless you draw a picture. So I'm drawing the picture as I discuss the problem. But in this problem, what I would be asking you guys is, what is the maximum height attained by the rocket? And what is the time that the rocket spends in the air?
So I just want to pause right there and say, considering what I said earlier, would any student say, well, good Lord, this has to be bigger than 9.8 or nothing's going to happen? So I'm not going to go back and check, but my suspicion is he said that the rocket accelerates at, rather than the force of this produces an acceleration of. Actually, even that's kind of complicated, right? So, he's drawing it so it's flying up, and I think that this is the actual thrust of this rocket must be enough, to, if there were no gravity, you would add 9.8 to this. And so I just wonder how you would deal with a student who says, what? I don't understand. And so it'll be curious to see, what vocabulary he uses later when he's addressing that. But I'm pretty sure he just said it causes an acceleration of, which, is just independent of what might actually be, the rocket might actually be experiencing. You can measure what something's acceleration is.
And I'm specifically asking those questions because you have to make a certain number of mental connections to understand how to deal with this question. So the problem wouldn't have a drawing with it to indicate where the separate parts are. So in this question, you're expected to recognize that there are really 3 different parts to this problem. There is the time in the problem where the rocket is under propulsion and is experiencing 1 acceleration. There is the time in this problem where the propulsion has turned off and is experiencing a different acceleration. And then there's the time in which the rocket falls back to the ground.
Cool.
Still experiencing the same acceleration as when it was moving upwards.
So it's interesting, right? And you can hear the slight pause in his voice. I think that some people would lump this portion with this portion, because they're both essentially experiencing the same acceleration. But I think that what I really love about what he's doing is he's talking about how, you might not have a drawing, but you really need to understand the various aspects of this. And of course, the drawing really helps. Like, okay, why? And some students would say, wait a minute, well, if that's when it shuts off, it should just immediately fall back down. And so he's really giving some excellent clues about the ways to think about this problem. I love that.
Now, you have options on how you can move forward to solve the questions of how high does it go and how long is it in the air. There's not a single right way to go here, but probably 3 or 4 different ways you could get to each of these answers.
That's great.
I'm going to present the same way that I did the last time. Or maybe I'll change it a little bit. I don't know. Tell you what, I'm going to change it a little bit. I want to prove that you don't necessarily have to do it the same way. I'm going to break the problem up into these 3 parts. There's the part where the rocket engine was firing. There's the part where the rocket engine had shut off, but we have not made it to its maximum height yet. But there's also the part where the rocket engine shut off, the rocket went to its max height, and came back to the ground. We can find all of that time in a single effort. So I'm just going to do the problem a little differently than I did it last time.
Just a quick commentary on the technology that he's using. I think that this is the type of technology where he basically doesn't have a pointer. So if he wants to attract someone's attention to something, he literally needs to add another mark to the page. And I've done that before. I can't remember which software I had that worked that way. Man, I just ended up making all these tiny little marks. And so I really like it when the software allows you to have basically a pointer or a mouse or something, because a couple of times there he said this, and I assumed he was pointing at this. And so I think that, he does a really great job with his vocabulary, indicating what he wants people to be thinking about. But it caught my eye about not having a pointer.
To offer you an alternative. And I'm going to say that these are the 3 parts of the problem that I'm going to do. You don't have to do it this way. The way I did it in class was a little bit different. But this is the way I decided to do it.
I see what he's doing. So I was a little bit confused at first because it seems like he's doing this little portion twice. He's doing it here and he's doing it here. But I can see what he's going to be doing. This is an interesting midpoint, or somewhere in the center point of this whole trajectory. But it's interesting because people want to know how high it gets. And so that'll be one approach. And then when he turns around and does this, he'll be able to recycle any of the math that he did here, just let time extend a little bit longer and have the final height be a different answer. That's really cool.
Now, what you might not understand is that each one of these parts is probably going to require its own set of motion variables. If it hasn't come through yet, let me kind of just hit you over the head with it. You need a different set of motion variables for any 2 time periods being observed.
Cool.
Anytime there's different accelerations being observed.
For sure.
Or anytime there's different displacements being observed. Or any combination of the 3. So, in this case, there are different ways to break this problem up, but each one of them is going to require a set of motion variables that we will then use to kind of solve for missing information. So I have one there.
All right, I'm just going to fast forward here a little bit
to
see what he's up to.
Displacement.
Oh, I see. Yep.
Here's where
one for everything. I just want to get to where he starts doing one of them.
And because they're vector values, they beg the idea of direction. We're doing one-dimensional motion right now. So because it's one-dimensional motion, direction is completely
right about there.
Direction has to be positive.
And interesting.
That's enough. Let's work this problem out.
Look at this blue here. That's super interesting.
I need something that gets me the displacement and something that gets me the final velocity. So let's deal with the displacement first and ignore the final velocity.
Love that.
That sounds like this relationship would probably be the most likely one to get us there. I will allow a 3x5 index card on your test tomorrow. So, again, I don't want to do the math. I'm only doing the math because I need you to see something. But ultimately, I would generally not want to do the math. 2 squared, 4. 4 times 4, 16. Half of 16, 8. So I'm pretty sure we're looking at a -8 meters here.
That side convention is so cool.
So,
All right, I think I'll stop right there. I really, really loved how he set this up. I loved how the colors came in to really help us understand what's going on. I think that there's some subtleties that I'd love to explore with that, because 8 meters or 2 seconds is actually long enough or far enough that the mass change of the rocket would in reality would be big enough to have to matter. But, as long as you keep this small and hope that this is small enough, this is probably, well, it depends what kind of rocket we're talking about, but it could be smaller than the size of the rocket. And then, the questions of how fast it'll be going and then how high it's going to go. So, there's some issues about when these equations are applicable, right? Because there's no air resistance built into this either. But I really, really love just the breakdown into the 3 different sections and really talking about how you needed a different set of variables for all 3 of these things. That was really, really cool. All right, everybody, I hope you have a great day. And remember, physics teachers are awesome.